Hello everyone, this is part 3 of the 1D motion video. And in this video, we are going to talk about the most important 1D motion called free fall. So first, what is a free fall? Free fall is defined as an object falling in the vertical direction without air resistance, without experiencing any air resistance. So here is a picture for the situation. So let's say here is the object with mass m, and it's moving in this vertical direction. So I can draw its velocity vertically. And you can say this velocity is Vy. Okay, so usually people use y direction for the vertical and x direction for the horizontal. So that's why we call it Vy. And then the acceleration here for the object is due to the gravitational force on the Earth's surface. And that gravitational force, we'll talk about this in the future chapter, will produce an acceleration for this object that is called Ay. And Ay has a value equals 9.8 meters per square second on the Earth's surface. And that, according to this direction, let's say I pick the y-axis to be downward. Origin O is somewhere above, and then this Ay will be positive, right? Because this direction is the same as the positive y direction. So in this case, it's positive 9.8 meters per square second. So let's call the free fall when the acceleration equals 9.8, which we call g. G is the gravitational constant on the Earth's surface. Okay, so again, the value here would mean there's no air resistance. But that is actually an ideal situation. We'll talk about actual situation in the later part of the video where there's the air resistance. So right now it's ideal. So imagine the object is moving in a vacuum, then that would be the case here. Okay, so ideal case corresponds to vacuum. All right, so let's call it free fall. And that's the most important 1D motion. So first, there is a 1D motion with acceleration equals whose magnitude equals g okay, so now think about the kinematic equations that we can apply here. So we can calculate, let's say, any instant velocity, we call it Vy, and it will be equal to the initial velocity, Vy naught, plus Ay times t minus t naught. Okay, so t naught is initial instant, and Vy naught is initial velocity. And in our case here, when we set the y-axis to be downward, we get positive g t minus t naught. Okay. Now, when we talk about the y position, then it will be about the displacement, right? So y position will be initial position plus the contribution of this vy naught and plus the quadratic contribution from the ay term. Okay. Now in this case, when we set the y-axis to be downward, we have y naught plus vy naught t minus t naught, and then plus 1/2 g but of course you also have the other important equation for kinematics. So vy squared equals vy naught squared plus 2ay y minus y naught. You also have that equation that you can use to solve the free-fall problem. But another thing about the what if I build the y-axis in the opposite direction? So what will happen to all these equations that we used here? Now here is still the same mass. Doing free fall, and then there's a vy, and now ay is also still this way downward, but we build the y-axis to be upward. Now what will change from the previous expression? So now we see the vy here now will be negative. Okay, now ay here will also be negative, and ay equals negative g, okay, equals negative 9.8 meters per second. So we kind of use this g here as a constant 9.8 on the Earth's surface, so that we have a symbol to represent this number when we talk about some equations. Now we still have the like vy final velocity as the function of the initial velocity plus ay t minus t naught. But now be careful, ay will be negative g, so minus g t minus t naught. Okay, so that will be the expression that we have for this coordinate system. And then the y position will be y naught plus vy naught. And also in actual calculation, the vy naught here need also to be given some sign here, a negative sign probably, if the object move downward with some initial velocity, which is non-zero, then you need to add a negative sign here when you plug in a numerical value. And we'll see that example later on in a practice problem. So t minus t naught, and then the ay contribution will be minus 1/2 g t minus t naught squared. Okay, so that's the negative sign here according to this setup. And similarly, for the vy squared, we have negative 2 g t minus t naught. Excuse me, y minus y naught. All right, so let's call the free fall in vertical 1D motion without air resistance. But let's also this free fall on a slope. Let me call this free fall on a slope. Now here's the picture. There's a slope which is smooth, and it makes an angle theta with the horizontal. The objects here So a smooth slope means that there's no friction force on the surface. Okay, so we talked about that in a future chapter. What's the meaning of that? It basically means that there's no friction on the surface. Plus the condition that we used in the vertical direction, there's no air resistance. Then we have a situation here. Okay, so now when we build the coordinate system, we'll build the x-axis along the slope direction. Okay, so it could be this way here, but you can also, for example, draw a different picture. Build the x-axis pointing upward. It doesn't matter. We should get to the same result. But here is the coordinate system. You can also build it this way. So always at a, let's say bottom, and then x-axis pointing upward along the slope. And the object here is sliding down without air resistance. Okay, so it's going down like that. So that's the velocity Vx, and that's the velocity Vx here. And if I draw the ay, then ay will be downward. Ay will be downward along the slope. So now in this case, it will be positive because it's in the same direction as the positive x-axis. But in this case, ay will be negative, right? Because it's against the x-axis. Okay, so now we can also use this angle theta to write down the actual expression for this ay. Now in this case here, ay is given by g sine theta with a positive sign. Okay, now in this case here, ax, since I already called it x-axis. Okay, excuse me. So that's ax. So ax is negative g sine theta. Okay, so in this case, it obtains a negative sign because positive x-axis is upward. And then this 1D motion should have exactly the same kind of equation that we have previously in the vertical direction, except that we need to change the previous g to g sine theta. Okay, so that's the only replacement there. All right, so that's the free fall case. It's ideal. Now let's talk about in reality, an object falling down, let's say from the sky, and such a fall should experience resistance. Fall with resistance. Now with this air resistance, let's say an object is falling down this way, okay, then it should experience an air resistance. There's a force due to the air resistance. Usually we call it G, means air drag. Okay, and such an air drag, such a force produces an acceleration. For this object, let's call it AD equals a constant c times the velocity squared. So velocity refers to this velocity. Okay, so I'm going to change the axis here. I'm going to call it the x-axis. Right, so again, that shows us the freedom in labeling the physical quantities we want to have the x-axis here, so we call it vx. And then there will be the vx here. Okay, so vx squared times a constant c give us the acceleration due to the air drag. Okay, so now I'm going to build a coordinate system downward. We call it the x-axis. Okay, but this object also experienced the acceleration due to the gravitational force. So let me write this down here. So that's also the gravitational force. Let's call this Fg. And it produced also an acceleration. We call it, let's call this Ag equals G, which is a constant. And also, because our setup here, it should be positive, right? Positive G, which is a constant on Earth's surface. And this AD here, since it's a resistance, so its direction is upward. So let me add the important negative sign here. Okay, so let's draw these two vectors, the two accelerations. AG is downward, okay, and AD is upward. Okay, now usually AG will be greater than AD, especially at the beginning, right? Because at the beginning, the velocity Vx is small, so usually, so initially, AG's magnitude is greater than AD's magnitude, since Vx is small. Okay, so that's why the total acceleration, well, when I sum them up, will be downward. Let me call this AX, okay, should be downward. And let's write down the AX expression. So AX equals, AY is, AG is positive, sorry. And AD should be negative. And let's write down the expression. So G minus C Vx squared. Now that's the change of the acceleration from the previous constant G in the previous free fall. So now we include this air resistance, CVx squared. Now this constant C can be determined from some experiment, which we do not plan to discuss here. We're going to just use these as a fact and then talk about how to solve the kinematics for this kind of acceleration. Okay, so now this acceleration is not a constant, not a constant anymore. So it will get more complicated. However, it's still solvable. So let's see. So now that is the total AX, and then according to the AX definition, which is dVx dt, so we're going to take a derivative of this Vx velocity, and that equals G minus C Vx squared. Okay, now in order to solve this equation for the velocity Vx, we need to separate the variables. Okay, so for people familiar with the differential equations, you probably know what I'm talking about here. That's the separation of variables. So you're going to move all the terms containing Vx to one side, and then the other side will contain a time, the other variable t. Okay, so I'm going to move all the g's to the left side, and then I get dVx over G minus CVx squared equals dt. Okay, so the separation of variables is like doing multiplications. Simply just multiply dt, because we know the derivative here is come from the ratio of two quantities, right? So that's why you can multiply the denominator to the right side. And then we're going to do integral. The integration bound depends on the initial condition. Okay, so let's say we have a free fall here. Let's start from 0 velocity. So at t equals 0 second, the object is at the origin, and then we x 0, we x naught here equals 0. Let's simplify our integral here. Okay, so let's say we have t equals 0 here, and then the lower bound here for the velocity will be also 0. And then we need to integrate to time instant t, and then that's the Vx. Okay. We can also change the variable. So let's say I want to differentiate between the integration variable dt here. So I'm going to call this dt prime, and this is Vx prime. That's Vx prime squared. Okay, that's just like a variable, a symbol, simply a symbol. You can change to any quantity you want to call it. You can also call it like dy, etc., dx. Okay, so the right side is very easy to integrate. We simply just get t here. Now the left side, let's see how we get the integral for the left side. The left side, we need to separate this. We need to turn this quadratic term into the difference of two terms. Okay. All right. So now, for people not familiar with the integration detail or not interested in the information integration detail, you can skip forward. But for people interested in knowing how to do this integral, you can keep watching this video. Okay. So I'm going to rewrite this as. Before I do that, let me do a side work here. So 1 over g minus c Vx prime squared equals. So I'm going to turn this into a product. Square root of g plus square root of c Vx prime times square root of g minus square root of c Vx prime. And then I will separate these two factors into the following. So if I look at like 1 over square root of g plus square root of c Vx prime plus this term, the subtraction term. So if I separate these two factors into these two independent terms, then I can do some calculation here, and then you will see that the denominator, if I combine these two terms, the denominator is exactly the expression that we get here. And the numerator now will have a factor 2 times square root of g. Okay, and that's some like additional term, so we need to divide it by 2 square root of g, so that we get exactly the same expression as before. Okay, so that's what I'm going to copy here. So 1 over 2 square root of g, and then by doing this, now we reduce the order of the denominator into the first order, so we can integrate that easily. Okay, because we know the 1 over x integral, right? That gives us a log. Right, so let me also write another note. Right, note 1 node 2. So if you do integral 1 over x dx, it will give you log x, natural log x. So that's exactly what we have here. And then we need to be careful about the coefficient. So let's say you have a coefficient, let's say c here. Then you want to have a 1 over c here in the final result. And that's exactly what we have here, square root of c. So that's why the final result is given by 1 over 2 square root g and c. C come from this factor and also left factor. They're the same. So put them together is a common factor. And then there's a log. X prime goes from 0 to Vx. Okay, so now we can plug in the numbers, and then we will get the following final result from the integral. And excuse me, that's a negative sign here. Yeah, I think I made a mistake here, because the so from this equation, right, so you need to have, let's say, 1 over c in front of the final log. And for the second term, that's a negative sign. So we should have a negative sign here. Okay, so that's why when I plug in the upper bounds, I get square root of g plus square root of c times vx divided by corresponding term here. And then when I plug in vx prime equals 0 here, they will cancel out. These two terms cancel out. So that's why the final result is here. Okay, but that doesn't look pretty. So let's look at a function definition. It's called a hyperbolic function. Okay, and then there's a definition of the tanh function. And let's say there's a tanh function, tanh x is defined as the ex minus e minus x over ex plus e to the minus plus e to the minus e negative x. So that's the definition of a tanh function. So let's compare it to our case here. So in order to get that form, we need to multiply this factor to the left side, t, which is t, and then take I also get rid of this exponential, the natural log, and then it turns into an exponential. So let me explain here. So we have square root gc times t equals a log function. That's what we have here. And then let's put both left and right side in an exponential, natural log. So put it natural exponential. And then the left side, let's keep that left side, and the right side here now becomes and if I solve for this Vx, I will skip the intermediate steps, but that's the like a linear equation. You multiply this denominator on the left side and then you solve for Vx. Turns out Vx to be the following expression: square root of g over c, and then minus e to the negative square root of gc times t, and then in the denominator we have a plus sign. It's just that the coefficient now is more complicated than the previous one. In the definition we have 1 there. Now the 1 there is replaced by square root of gc. Okay, but the result is basically the same because they have exactly the same form. Okay, so that's why we can replace all those things, the complicated expression there, by tanh the hyperbolic function, and then square root of gc times t. Okay, so if you are familiar with the tanh function, then you can use this directly. Otherwise, you can just go back to the previous the definition of the tanh function and then plug in the t, like any instance t, then you can calculate the velocity at that instant. Okay, and we can do this further to integrate out the velocity so that we get to the position. Okay, so dx dt equals Vx equals this whole expression. Then we can do again the separation of variables. So we can do dx, leave dx on the left side, and then the right side becomes tanh dt their integral. Okay, and then we start from 0 position, 0 instant, and then go to the t instant, x position. Also changing variables here to t prime so that we don't get confused. And then again, there's another side note here. So if you integrate a tanh function, then you get give me a second. You'll get log function of a cosh. Okay, so simply just the mathematical integration, you can find this result from some integration table. Okay, so what's cosh function? Cosh function is defined as ex plus e minus x, e to the minus x divided by 2. Okay, so that's the cosh function. And then we need to plug that in this log function. Okay, so that's why, so let me write down the equation result. So x now equals the coefficient here. Now we need to copy that. We still need to copy that. And then we also need to copy the effect of this coefficient, the square root of gc, which becomes 1 over square root of gc when you do the integral, and then log function, natural log a cosh function. Okay, and then when you plug in the t equals 0, t prime equals 0, you get 0 here. Okay, so the tanh function, you plug in 0, 0, then they cancel out. Okay, so that's why it becomes 0 here. we don't need to, for cost function, yeah. For cost function, it becomes 1. When you plug in t equals 0, you get 1 here, 1 here. And then you get log 1. Log 1 is 0. Okay, so that's why we can neglect that. All right, so that's the final result. Okay, but again, if you're not familiar with the cost function, you need to expand it into this form. Okay, and then plug in the time instant, and then you can calculate the position. Okay, so we still need to simplify this prefactor a little bit because square root of g will cancel out. Okay, so we get 1 over c instead, log function cos square root of gc times t. Okay, so that's the position as a function of time as given by this equation. All right, so let's talk about the limit of t goes to infinity. Okay, so let's say you put an object at infinity, and then you will start to move downward, and then the time here can be infinity, goes to infinity. So in this case here, you can see when I plug in infinity here in the width expression, the second term disappears. Okay, so what we have here is Vx approaches this prefactor, and then there's there are 2 terms, they cancel out. Okay, so but as I said, the other 2 terms, they become 0. So that's why we have square root of g over c as the final velocity. Okay, and that's called a terminal velocity in a vertical fall with air resistance. So the gravitational constant g and the air resistance coefficient c come in play here. That computation gives us this terminal velocity, and this velocity cannot change anymore, right, once the c is fixed. But you can also actually figure out this terminal velocity before we did all these methods. We can look at this equation here. So the terminal velocity means that the final velocity when it's not changing anymore, right? So if in the end Vx is a constant, okay, then that would mean the total acceleration will be 0. And total acceleration comes from the summation of these 2, right? So that means that the g minus c Vx squared equals 0. So that's why we can solve for Vx, which is square root of g over c. Okay, so that's called again terminal velocity. Okay, so that's exactly the same as we discovered here. Okay, so terminal velocity is easy to find, but if you want to find the exact expression for the velocity at any instant and also the position at any instant, then you have to go through this complicated integral. Okay, so that's the free fall discussion, and also the falling with air resistance discussion. All right, that's all for this video. Thanks for watching.